Hello and welcome back, everybody. Today in calculus, we are going to actually put it all together, with all the stuff that we've been learning about sequences and series, convergence and divergence. I want to know now, how do we apply it to the calculus stuff that we have been doing, okay? So today we're going to be talking about something that is known as something that's called the power series, and also the radius or slash interval of convergence for the power series then, okay? So as a kind of a recap first, what I want to talk about are the following. You'll know that if we have 1 over 1 minus x, that is supposedly equal to 1 plus x squared plus x cubed, and so on and so on and so on, which is equivalent to the summation of n is equal to 1 to infinity of x to the n. Now, this right here is something that we derived from the geometric series because on the right-hand side, you'll notice that it is something that is geometric because you're multiplying x in order to get from one term to the next. And in terms of a geometric series, for where it converges to, well, it converges for when the radius is supposed to be less than 1. So what that means is for this right here, for this equation to be true, this works for all of the values of x that is going to be between 1 and -1 because x, again, remember, is supposed to be my radius. And for any geometric series, if the radius is less than 1, the absolute value of it, then therefore it converges. And it converges to a over 1 minus r, which is basically equivalent to what I have on the left-hand side. So meaning if I were to, graph both of these equations, then that means that they are identical to each other so long as it's x that is in between -1 and 1. So here, let me just kind of go ahead and give you an illustration. If I go to decimals over here, you'll notice that on my first equation, we have that 1 over 1 minus x right here showing. Now I'm going to go ahead and introduce the second equation, which is the summation one that I just showed you on the right-hand side. That is what is known as the power series. Here we have n is equal to 0 all the way to the fourth term. So when n is equal to 4, you get that part as a polynomial. You'll notice the two graphs are almost identical to each other, so long as your x value, as we said, is between -1 and 1. Everywhere else, it's going to look different. As I take that series and I increase the number of terms so that it gets bigger and bigger, then the two graphs are going to become more and more alike. So for example, n is equal to 5, and then n is equal to 6, and n is equal to 7, n is equal to 8, and so on and so on. So you can see, so long as, again, you're between -1 and 1, the two graphs are almost identical to each other. The red graph is basically kind of like hugging the blue graph. So then that means that they are pretty much equivalent. And then similarly, now if I go back over here, the one that we also talked about, but not as much, is this one over here underneath. E to the x right here, we derived it a long time ago. That is equivalent to 1 plus x plus x squared divided by 2 factorial plus x cubed over 3 factorial plus x to the 4th over 4 factorial, and so on and so on and so on. And that as a series is supposed to be the summation from n is equal to 1 all the way to infinity of x to the n divided by n factorial. Actually, I just realized there's a small little mistake that I need to change. These are all starting at n is equal to 0 as my first term. So got to watch out for that small little piece, okay? So what that means is that, again, e to the x, this right here, is then equal to this guy over here. But just like what's on top, it doesn't necessarily mean that all values of x actually works out, because maybe it only works for certain values of x. Maybe it only works for, like, say, an interval of x, or maybe it works for all x. The question is, well, how many values of x does it actually work out for? Okay, so here, what we can do is we can look at that in just a little bit, actually, because I don't want to spoil the surprise for you for just yet. Okay, so that's what I need to talk about for today. Okay, so the idea over here is we're introducing something called the power series. And the power series, right, centered at x equals to a, is basically a series that can be written in a form just like below. So you'll notice that we have some sort of like c of n multiplied by x minus a raised to the nth power, summation from n is equal to 0 to infinity. So if I were to kind of write all that out, this is what it looks like on the right-hand side. So any equation that can be written in this form right here, where you have infinite number of terms, then that is going to be called a power series. And the center of it, meaning the middle of everything, is going to be at x equals to a. Okay. So in the case of above over here, then that means that for this equation, 1 over 1 minus x, the center is supposed to be at 0 because you can notice right here, it's supposed to be x minus 0 raised to the nth power. So that means in the middle, x equals 0, that is going to be my center. And there is an interval of convergence or radius of convergence for all the values of x that is going to work around that center. So this right here is what is known as the radius of convergence because, that is going to be my interval of convergence, because meaning that's the values of x that are going to work then. And notice here that at x equals 0, that's going to be my center then in this case, okay? So the question is, okay, well, if I take any function and I write it as a power series, how do I know for what values of x is it going to be convergent to? So how do I know the two are going to be identical for what values of x? So there are a total of 3 cases that we have to consider. Case number 1 is that it only works at a single point. Well, it doesn't really do too much in that case, but sometimes it does actually happen then. Case number 2, it works for all values of x. And so that would be the ideal case because then I can plug in whatever I want for x in each equation. It'll still be the same thing. And the last one will be only for a certain interval of x. So that is the case of, like, say, the very first one with 1 over 1 minus x then, okay? So we need to figure out which one is going to happen depending on what equation we have. All right, so let's go ahead and jump into it. All right, so here are a few examples of this whole interval of convergence thing. So in these examples, here's what I want to do. I want to find the interval of convergence for each of these power series. So each one of these power series, right, is equivalent to some sort of function that as of right now, we don't know what is it yet. But what I want to do is I want to find out what is that interval of convergence where the two are going to be identical to each other, where that function is equal to this power series. So the way that we can solve for this is we can look at it using the ratio test. Okay, we can look at it using the ratio test. If you recall, the ratio test says that if you look at the next term divided by the current term as the absolute value, and then as n approaches towards infinity, that is supposed to that ratio, if it's less than 1, then it's going to be convergence. So that's something that we can kind of work off of. So here, let me go ahead and set that up then. So first, we're going to go ahead and write the limit as n approaches towards infinity of the next term divided by the current term. So then that means I'm looking at this as a ratio test and I'm hoping that it does converge. And I need to figure out where is that convergence going to be then. Now, since we're applying the ratio test, and that means that this guy has to be less than 1 then. Okay, so that's the key thing because I need to make sure that converges. A of n is going to be this equation over here. So let me just kind of write that over here if it helps out a little bit. Okay, so now let's go ahead and write out each part. So limit as n approaches towards infinity of a of n plus 1, the next term. That's going to be x minus 2 raised to the n minus n plus 1. All divided by n plus 1. So that's a of n plus 1. Divided by the current term, which is supposed to be x minus 2 raised to the nth power divided by n. And then supposedly it's going to be less than 1 once again. Clean up the algebra inside right here just to see what happens. Limit as n approaches towards infinity. Let's see, the bottom part and the top part. Let me go ahead and put all the like terms together. If I put all the n's together, we will have n divided by n plus 1. Multiply by, if I take all the x terms and put those together, we would get x minus 2 raised to the n multiplied by x minus 2, all divided by x minus 2 quantity squared. So the top part right there, the numerator, that is because this guy right here is equivalent to this guy. Notice what I did was I extracted out the plus 1 just so I can match up with some of the terms that I have. Whereas the other part, x minus 2 to the nth power, that's going to be this guy over here, okay? So when I write it this way, you'll notice that, yeah, x minus 2 to the n, they cancel out from both top and bottom, so that's actually really good. Now, what we have left now is limit as n approaches towards infinity of n over n plus 1. And I'm noticing that we have the x minus 2, which x has nothing to do with n, okay? X has nothing to do with n. So what I can do is I can actually take that out of the equation like this, okay? So keep it isolated if you want to say that. Now, as n approaches towards infinity, we're really just focusing on this part right here. And as n approaches towards infinity, that really just gives us 1, which is really good because now we have something nice and simple. the absolute value of x minus 2 is less than 1. And that is something that we can definitely solve for to give us an idea as to where this interval of convergence is going to be. So if I were to kind of like, keep going to simplify this, we can say negative 1 is going to be less than x minus 2 is going to be less than 1. And then finally, if I add 2 to both sides, we have 1 is less than x is going to be less than 3. So that right there, that's going to give me my interval of convergence. Now, this is the part where you have to be very, very careful, because if you recall that when the ratio is equal to 1 for the ratio test, it was supposed to be inconclusive. And so what that means is, in this case, we actually have to test the endpoints to see, does it work or does it actually not work? So as of right now, we know that my interval convergence is between 1 and 3. So that means if I plug in any values between 1 and 3 for x, then this supposedly is converged. Well, let's go ahead and see what happens on the side at those endpoints then. If x is equal to 1, right, on the left-hand point, I'm going to go ahead and throw it into the equation. The summation is then going to say 1 minus 2 raised to the nth power divided by n, for n is equal to 1 all the way to infinity. And if we clean that up, it's going to be summation n is equal to 1 to infinity of negative 1 raised to the n divided by n. And this right here is going to be something that is going to be convergent because it's an alternating series test, right? So by the alternating series test, then this is going to be convergent because it's also an alternating harmonic series, okay? X equals to 1 is in the x is equal to 1 is convergent, I should say, okay? X is equal to 1 is convergent. Okay, next, we're going to go ahead and try the other endpoint. So now for x is equal to 3, we're going to go ahead and plug that into our equation. So that's going to give me the summation of n is equal to 1 all the way to infinity of 3 minus 2 to the nth power divided by n. So that is going to be equal to the summation of n is equal to 1 to infinity of 1 over n. And this right here, this diverges because of the p-series test. Okay, so there it is. Now we can actually use all of those tests that we learned to determine where is it going to be, if the endpoints are going to be convergent or not. So therefore, in the very end, okay, my interval of convergence is going to be from negative 1, inclusive of it, because of what we just showed, is less than or equal to x is less than 3. So that is going to be my interval of convergence, okay? And if you're thinking about the radius of convergence, well, that's going to be from the center all the way to the end of the interval. So that means my radius of convergence, my middle is at x is equal to 1. So then that means my radius of convergence must be equal to 2, because 1 plus 2 is equal to 3, and 1 minus 2 is equal to negative 1 then, okay? So those are going to be your two answer in this case, okay? So there it is. All right, now let's look at another problem using the same idea to see how to find the interval convergence in this one. So this time around, I have something that's similar. What I want to do is I want to find the interval convergence. So once again, we're going to go ahead and set up the ratio test. Limit as n approaches towards infinity of the next term divided by the current term. So just writing it all out. So first I'm going to put in the absolute value. The next term is supposed to be 4x plus 1 raised to the n plus 1, all divided by n plus 1 raised to the third power. All that is divided by 4x plus 1 raised to the nth power, and then divided by n cubed. Okay, and that is supposedly going to be less than 1. So we're going to clean up the algebra here. So limit as n approaches towards infinity. I'm going to combine all the terms together that are alike. So let's go ahead and put n cubed on top, and we're going to have n plus 1 cubed on the bottom, on the left-hand side. Multiply by, let's see, it looks like we have 4x plus 1 raised to the nth power multiplied by 4x plus 1, same as last time, all divided by 4x plus 1 raised to the nth power. And all of that, once again, is absolute value and less than 1. The terms that are going to cancel out is going to be the 4x plus 1 to the n for both top and bottom. And whatever I have left, that's what I'm going to focus on as n approaches towards infinity then. Okay, so let's see, limit as n approaches towards infinity. We have n cubed divided by n plus 1 cubed. And then we have the 4x plus 1, which I'm going to isolate because it has nothing to do with n again. And all that is less than 1. And fortunately, in this case, as n approaches towards infinity, the n cubed divided by n plus 1 cubed, that goes to 1. So we can go ahead and write that in there. 1 multiplied by the absolute value of 4x plus 1, absolute value is going to be less than 1. And right there, that'll give us an idea as to like where to go then. I am going to get rid of the absolute value by making negative 1 is less than 4x plus 1 is less than 1. Add 1 to all the sides. So, minus 1 from all the sides. So negative 2 is less than 4x is less than 0. So x is going to be in between 0 and also looks like it's going to be negative 1/2. So once you get that, that'll give you, again, your interval of convergence. But remember, you need to check the endpoints once again. So we're going to go ahead and look at the endpoints. Okay. For x is equal to negative 1/2. That is going to give us the summation of n is equal to 1 all the way into infinity of negative 2, looks like, and then plus 1 to the nth power, all divided by n cubed. And if we simplify that, that gives us summation of n is equal to 1 all the way to infinity of negative 1 to the nth power, all the way divided by n cubed. So this right here, by the alternating series test, this converges because, well, we have an alternating series test that tells us that, yeah, it's convergent. Now we're going to have to check the other endpoint, okay? So now we're going to look at x equals to 0 and see what happens when I plug that in. So that's going to give us summation of n is equal to 1 all the way to infinity. And if I plug in x is equal to 0, that's going to give me 1 to the nth power divided by n 3 to the n. And this right here, this is supposed to be convergent as well because it looks like this is a geometric series right here. So by the geometric series test, r is going to be absolute value of r is less than 1/3, so therefore it's going to be convergent. So that means that my interval of convergence is going to be, we're going to include the endpoints in this case, negative 1/2 is less than or equal to x is less than or equal to 0. So there it is. And if you're thinking about what's the radius of convergence, well, again, look at where the middle of that is, which is going to be 1/4. And then from there to the endpoints, looks like you're going to have to add 1/4 or subtract 1/4. So the radius of convergence is going to be equal to 1/4 then. Okay. All right. Now here it is. We're going to look at that one case, as we said from the very beginning, where we're looking at the power series of e to the x. I want to know for what values of x is the e to the x equal to this power series. Well, let's go ahead and apply our ratio test and see what happens. And by the way, feel free to try it out on your own and see if you can come up with your conclusion also if you want to do that. If not, let's go ahead and get started. Limit as n approaches towards infinity. Absolute value of the next term, which is x to the power of n plus 1, divided by n plus 1 raised to, factorial. And all that is divided by x to the n divided by n factorial. We're going to go ahead and combine the like terms just what we've been doing so far. So we'll put the n's together. We have n factorial on top. The bottom part, the n plus 1 factorial, I think I'm going to go ahead and write that as n plus 1 multiplied by n factorial. So then that way we can extract the n factorials to be canceled. Multiply that by, on the top, we have x to the n multiplied by x because I'm changing that x to the n plus 1. And then all of that is divided by x to the n. And supposedly, it's less than 1. Okay? All right, we're going to go ahead and clean some of this stuff up. The n factorials can cancel out. The x to the n, x to the n can cancel out. So all that we have left now is limit as n approaches towards infinity of x divided by n plus 1 is less than 1. Now this is the part that's actually very interesting because normally I would extract out the x. But if you notice that regardless of if I extract out the x or not, as n approaches towards infinity, this is going to be equal to 0, the limit of this, because the bottom is getting bigger and bigger regardless of what x is, and 0 is always less than 1. So what that means is that it doesn't matter for what values of x you actually use, this is always going to be true. So therefore, my interval of convergence is going to be x is going to be all real numbers, because there's no restriction that we can solve for x like we did in the first case. And finally, let's just go ahead and check one more time via decimals so you can see that it's true then. So here's your graph of e to the x. And underneath right here, you'll notice that we have the power series for the endpoint being for using 3 terms. Now, if I take that and change it, let's go ahead and maybe make it so that it's like 4 terms, just to see what happens. So n is equal to 4. And then n is equal to 5, n is equal to 6. And you can see as I increase the value of terms or the number of terms, the two graphs are becoming more and more alike also. And on the left-hand side, it's becoming more and more flattened, so it becomes the e to the x graph. Let's go ahead and put in 80 just to see what happens then. Then now you can see that the two graphs pretty much overlaps. And if I put like 800 or 8,000, then yeah, the two graphs are pretty much all identical. And it's not just within a certain interval, it's for all values of x. So there you go. That's going to be our conclusion then. So if we go back over here, let me just kind of fill this in because this is something that we can definitely use in the future. The interval of convergence over here is going to be all real numbers. So meaning no matter what you use for x, the two are going to be identical to each other. All right, thank you so much for watching. I'll see you guys next time. Bye.